In this video, I'm going to show you how to solve Legendre homogeneous differential equation. The Legendre differential equation is a second-order ordinary differential equation which can be written as this. For reducing this equation to linear differential equation with constant coefficients by the substitution, we assume exponent to the power z is equals to a plus bx, and by solving this, by taking ln on both sides, we get the value of z, which is z is equals to ln a plus bx. By solving the equations as we have discussed in the previous video of Cauchy differential equation, we'll get our final answer, which look like this: a plus bx dy by dx is equals to b dy. Likewise, a plus bx whole square d square y upon dx square will equal to b square d minus 1y. And for cube, a plus bx cube dqy upon dx cube is equals to b cube d minus 1 d minus 2y. And similarly, a plus bx to the power n dny upon dxn is equals to bn d minus 1 d minus 2 to d minus n plus 1y. Okay, now I'm going to show you an example how to solve Legendre differential equation. So let's say this is my differential equation, and I'm going to solve this by Legendre differential equation method. First of all, I will assume e exponent to the power z is equals to 1 plus x. I will assume this term is equals to e to the power z, and by solving this, I'll get the value of z by taking ln on both sides. So the value of z will equals to ln 1 plus x. Now I will find the roots of the equation, and before finding the roots, I will convert this equation in the form of this: b squared d minus 1y for the square term, and b dy for this term, and y as it is equals to 0. For finding the roots, I simply replace the value of b in this equation and solve this equation, and my roots are come out to be plus minus 1 iota. So the complementary function of this equation in the form of z is yc is equals to c1 cos z plus c2 sin z. Now I will replace the value of z from here. Let me show you from here. So my complementary function will become c1 cos ln 1 plus x plus c2 sin ln 1 plus x. Now I will find out the particular integral. The particular integral of this equation will be yp is equals to 1 upon d square plus 1 2 sin z. Now I will replace d square by minus a square, so my equation of yp will look like this. And by solving this, I get 1 upon 0 2 sin z, which goes to infinity. So if we have function of t is equals to 0, then we will take the first derivative of function of t. So I will take the first derivative of this function over here. I'll take the derivative of this function. Yp is equals to z1 upon 2d. The derivative of this is 2d, 2 sin z. Now 2 and 2 are cancelled by each other, and now I will multiply and divide by d. So my equation of yp will become z d upon d square sin z. Now again I will replace d square by minus a square. So I have a value of a is here, my a is equals to 1, so yp is equals to minus z d sine z. As we know that the differential operator, which is d, is equals to d by dz, which is a derivative. So the derivative of sine z is cos z. So my equation for yp is equals to minus z cos z. And now I will just simply replace the value of z over from here to write it in the form of x. So my yp will become minus ln 1 plus x cos ln 1 plus x. So the complete solution of the given equation will become c1 complete solution is equals to yc plus yp. So I'll just simply put the values of yc and yp. Y is equals to c1 cos ln 1 plus x plus c2 sin ln 1 plus x minus ln 1 plus x cos ln 1 plus x. Thank you for listening.